was also a well-known person in nuclear NMR. Then he did his postdoctoral work with Shimon Bega in Israel, a noted expert in UPR and NMR, and also with Richard Ernst, who got Nobel Prize in Chemistry for his contribution towards FT-NMR. After that, he joined as a research staff at the Francis Bitter Magnet Laboratory at MIT Boston, USA for 4 years. And then he returned to UK as a research fellow, Royal Society research fellow. To work in the Center for Superconductivity in Cambridge. Then he joined as a lecturer in the University of Stockholm in University of Stockholm, where he became the full professor in 1977. And now, and after, in 2001, he joined as a professor of physical chemistry at Southampton University. His major research interests are nuclear magnetic resonance. In fact, he had won many awards in this particular field. And he has also written a book on spin dynamics, the basics of nuclear magnetic resonance, which is a very received book, textbook. He has his other interests are structural biology, membrane proteins, spin dynamics, and nuclear magnets. And he has several awards to his credit on it. He was a fellow of the Royal Society in 2001. He was elected as a fellow of the Royal Society in 2007. He received the Ambre Prize from the International Society of Magnetic Resonance in 2005. The Gunther Lokian Prize in Nuclear Magnetic Resonance Spectroscopy in 2008. The Russell Varian Prize in Nuclear Magnetic Resonance, and several other awards. May I invite you, sir, to give your lecture?
Okay, thank you very much. So I will share my screen. Okay. Okay, so is this visible to you? Can you see this?
Yes, I can see.
Okay, well, thank you very much for that introduction, and thank you for giving me the opportunity to speak at the meeting. I apologize for not attending any of the other lectures yet, because the time difference makes it a little difficult, and I'm also in the middle of my teaching, so I apologize for that. But I will I'll give you a short talk now on some of our work on endofullerenes. The title of the conference refers to new materials for the millennium. I'm not sure if endofullerenes qualify in that respect, but certainly I hope you agree that they're very interesting systems, and that you will find something of interest in learning or hearing about some of the work in this area. I'm sure that most of you will be familiar with fullerenes. So C60, which is the seminal fullerene, was discovered in 1985 with a Nobel Prize awarded somewhat later. And as I think you will know, the molecular structure consists of closed cages of 60 carbon atoms in an icosahedral structure. And it was not long after the discovery of fullerene and its characterization that people became fascinated by the prospect of exploiting the cavity which is in the middle of this small cage. There's a hole in the middle which is about the size of a single atom or molecule. And the prospect was immediately appealing of trying to find a way of encapsulating atoms or molecules inside these cages. And essentially using these structures almost as test tubes to study molecules or atoms in something resembling isolation without being bonded to anything directly. And in fact, it was very soon after the discovery of fullerene that it was found that, just as an accident of the preparation process of in the laboratory of fullerenes, that sometimes fullerenes were formed containing metal atoms which had condensed out of the carbon vapor together with the fullerene, and in particular lanthanum was actually the lanthanum endofullerene was the first one discovered by the same group who had discovered fullerene itself. Somewhat later, it was also discovered that small amounts of helium or neon could also be encapsulated in the cage. At that time, these compounds were made by vaporizing carbon and then purifying the resultant black substance. A small amount of it contains C60, and if the fullerene is vaporized in an atmosphere of noble gas, then very rarely some of the noble gas atoms get encapsulated inside as well. So these were trace amounts, but enough to study. So, for example, only one helium in about 880,000 fullerene molecules. So, nevertheless, there was a series of papers studying these trace substances. Remarkably, it was also found that the helium endofullerenes with helium inside were even found isolated from very old rocks in Australia, actually, which are almost as old as the formation of the Earth. And in addition, the isotope ratio of helium-3 to helium-4 was found to be unusual, and there are speculations that actually these fullerenes did not originate on the Earth, but actually even before the formation of the solar system. So they originated in probably in carbon-rich stars, which then exploded in a supernova, and the solar system was formed together with its endofullerenes from the debris of the supernova explosion. So these extremely, by far and away, the most ancient molecules known, which even predate the existence of the solar system. Now, a breakthrough in the field was made by two Japanese researchers in the early 2000s, by Koichi Komatsu in Kyoto and his student Yasu Murata, who went on himself to found his own research group. And these two groups, they succeeded in encapsulating molecular hydrogen, H2, inside the fullerene, and later Yasu Murata's group encapsulated water inside fullerene C60. And these substances were produced in very high yield, essentially 100% yield, or 100% purity. So this is a very different matter from the helium endofullerenes, which are only available as trace amounts. The breakthrough which these groups succeeded with was a tour de force of organic chemistry, actually, in which they synthesized these molecules more or less de novo. This is a a sketch of what, from Yas actually, of what his group succeeded in. So the starting material was actually C60 fullerene, which is available commercially, and then a series of organic chemistry reactions attached extra groups to the cage, and in that process open an orifice, a hole through which the guest molecule can then be inserted, sometimes by high pressure or high temperature. And then a series of subsequent reactions can then be used to take off the exohedral groups and reseal the cage again, this time with the target molecule inside. And variants of this process have now been performed in different laboratories, including that of my collaborator Richard Whitby in Southampton, and a variety of different systems have now been produced. So just to give you a survey of the landscape as it stands right now, so in existence there's hydrogen in C60 and its isotopologues, so HD and D2 have also been produced in pure form. Water in C60 and some of its isotopologues, so D2O for example, and we've also studied the water with oxygen 17 in C60. A new system at the time, which is HF in C60, was produced a few years ago by Richard Whitby, student Andrei Krakmalnikov. This was a new material at the time. This shows you, actually, for those interested, this shows you what the substances look like in solution. They form purple solutions. More recently, Sally Bloodworth in Richard's group has succeeded with the first organic molecule encapsulated in a fullerene, which is methane in C60. And in addition, much effort has now gone into encapsulating noble gases inside fullerene, including helium-4 and helium-3, and also neon and argon. So unlike the very early work where these were produced by purifying carbon deposits formed in the presence of helium, these systems are now generated by organic synthesis and are produced in high yield in large amounts, so much more amenable to study by different types of spectroscopy and so on. And thus, this is essentially the basis of our work, is to work with these substances and to see what their properties are and what can be done with them. One can imagine, for example, that the HF in C60, HF has a dipole moment, an electric dipole moment. So essentially this molecule is a single electric dipole encapsulated in a cage, and which is free to rotate in all possible directions. And that's can be the basis of many different interesting molecular materials properties, such as a capacitor, as a dielectric material, possible ferroelectric material, and so on. And all those things are under investigation. So these substances then are symmetrical cages of carbons encapsulating single molecules or atoms. Actually in C60 only one atom or molecule will fit, although there is some evidence actually for very trace amounts of two heliums inside C60, but that's about as far as it will go. There are larger fullerenes which will encapsulate two atoms or molecules, but I won't talk about that here. As I said, they're purple solutions, and as solids they're very black solids, basically like soot. Their advantages from the purposes of applications in spectroscopy are that they're extremely pure. They can be made essentially in a completely pure form. They're completely homogeneous. So this is not like, say, carbon nanotubes, which are very hard to produce in a homogeneous form. They're extremely stable, so they can be studied by forms of spectroscopy or other physical measurements, all the way from millikelvin temperatures up to about 500 Kelvin. And they're now available in quantities of tens of milligrams, in some cases going up to a gram. And it's also possible to perform chemistry on the endofullerenes and attach further groups on the outside, functionalize them, react them in various ways, and so on. I won't be talking about that today either. This is just a taster, actually, of the sort of things which are being done with them. This is through a collaborator of ours, Andrei Klobistov in Nottingham in the UK. He's an expert on transmission electron microscopy with ultra high resolution, so on the level where you can resolve single molecules and atoms. This is a picture from his group, actually, an image from his group of a single-walled carbon nanotube. So that's the two lines here show the walls of the nanotube, and inside the nanotube are C60 molecules lined up inside, like peas in a pod. And this substance was made with HF in C60, so you can actually see the fluorine atom inside each C60. So that's the sort of level of imaging and study which is now available. And there, in fact, Andrei even has videos of these things rattling around inside the nanotube and sometimes fusing together under the influence of the electron beam, which is used for the imaging. What is the interest? Well, at the moment it's a little bit speculative. So far, remarkable materials properties of, I would say, have not of true interest to material scientists have not really been emerged. That may come. At the moment, the main interest is to do basic science with these materials. Essentially, one has isolated atoms or molecules, and they behave quantum mechanically in this highly confined space. And I'll be showing you what that means in a minute. An aspect which we've become increasingly interested in, actually, is that these systems enable one to study the interaction between a single molecule and a surface in great detail. And that's actually a topic which is hard to simulate by quantum chemistry techniques, but is of great importance to understand materials and biomolecules, is how molecules interact with each other, and to refine techniques for modeling those interactions. Another aspect which has become very interesting through some collaborations is to use these substances as substrates for lasers, solid-state lasers and masers, microwave and terahertz sources. And also more speculative, to use them as substrates for quantum information processing. And my particular interest is to use these to generate nuclear spin polarization. But I'll pass over that topic as well today. Now, the spectroscopic and other physical techniques which are used to study these systems at the moment are my own main field, nuclear magnetic resonance, in particular at cryogenic temperatures, but also in solution state, as is more common in chemical laboratories. Also with collaborators, infrared spectroscopy, and in particular terahertz spectroscopy, proves to be extremely interesting for these substances, either using continuous wave modes or very short terahertz pulses. We also use a lot of neutron scattering and also measure the dielectric properties of these materials. They're all interesting. So let me just start by looking first, showing you what happens for the simplest system. So helium in C60. So just to give you an idea, the animation here shows slices through the helium C60 molecule and shows the van der Waals radius, radii of the carbon atoms and the helium. And it's actually maybe a little surprising, at least it was always a bit surprising to me, that the helium is pretty tight in there. It's just a single atom, but there's not much room. There is room for the helium to rattle around, but not much. The inner radius of the C60 is an angstrom or so larger than the radius of the helium. So the confinement is tight, and that means that the helium behaves as a particle in a box, which those of you who've taken some basic quantum mechanics courses might remember exhibits is a classic case which exhibits quantized behavior. It's just that when you learn about a particle in a box, then the usual examples which are advanced are, for example, electrons trapped inside a box, something which is approached by the substances known as quantum dots. In this case, though, it's not an electron which is the quantized particle, it's an atom, the helium atom, which is much more massive than the electron, and that has an effect on the sort of energies that we're talking about here. So just to show you some basic measurements, I think many of you will be familiar with NMR, in particular carbon-13 NMR. So this is just the NMR spectrum, the carbon-13 NMR spectrum of helium in C60 in solution. There are two peaks because this substance is not completely pure in this case. The large peak here actually is from carbon-13s which are in C60 molecules, and the smaller peak is from carbon-13s which are in C60 molecules which have a helium inside. So we have the C60 molecules which have, some of them have a single carbon-13 and they give a peak here, and then the helium C60 give a peak at a slightly different chemical shift. The helium causes a slight shift of the carbon-13 resonance. It's a very small shift, of just about 20 parts per billion, but it's detectable in the spectrum, and this shift is also understood quite well using quantum chemistry. Now my student George has sharp eyes, and he noticed that for the helium-3 C60, after a great deal of optimization of the magnet homogeneity, he could actually detect a small splitting on the carbon-13 resonance of helium-3 in C60. That's a very tiny splitting of only about 75 millihertz. But that's actually due to a J coupling between the carbon-13 in the cage and the helium-3 nucleus, which is spin half. Hence you get a doublet. And that's actually the very first time that J coupling has been seen to helium-3. And it's also an unusual example of a J coupling in the absence of any formal chemical bond between the helium atom and the carbon cage. So the helium is completely free to rattle around. Nevertheless, there is a small J coupling to the carbon-13s, and that's something we are examining and have published recently. So let's have a look at the quantum mechanics of the helium inside the cage. So I start by discussing something which most of you will be more familiar with, which is the hydrogen atom. So the hydrogen atom consists of a proton and an electron. which are bound together by the Coulomb potential. So the electron is confined to the region of the proton by the attractive force between the opposite charges. Both of the objects have spin, which is actually not too relevant to us here. But the main thing here is that the electron is confined in a spherical region around the proton. And those of you who have done some quantum mechanics should be able to remember how this works out. You solve the Schrödinger equation for the electron going around the proton, and you come up with an energy level diagram and a set of quantum numbers, which for the hydrogen atom are called N and L, a principal quantum number and an angular momentum quantum number. For historical reasons, the solutions with L is 0 are called s orbitals, and solutions with L is 1 are called p orbitals. But you come up with an energy level structure which of course underpins all of chemistry. So this is the basis, this energy level structure is the basis of the periodic table, the basis of the modern understanding of how atoms and molecules work, and indeed all of chemistry. The energy scale in units of electron volts is around 10 electron volts in this case. And in spectroscopy we see transitions between these levels. So the light emitted by atoms, such as hydrogen atoms at high temperatures, is due to transitions between these energy levels. And that was in fact how the structure of the energy structure of atoms and indeed quantum mechanics was figured out in the first place. Now for helium in C60 it's not so different. This time we have a helium atom, not an electron, but it's also confined to a spherical space. And again one has the Schrödinger equation which one can solve, and one generates a slightly different but not fundamentally different energy level structure. Again, two quantum numbers, but the energy scale is much smaller. It's about 1,000 times smaller, mainly because the helium atom is much more massive than an electron. But the principle is the same, and one can do spectroscopy on the transitions between these quantized levels. It's just this would not be optical spectroscopy anymore with visible light, but terahertz spectroscopy with low frequency infrared light. So for example, if the sample is at very low temperature, then the molecules start out in the ground state, and then one sees a single transition to the first excited state, but as the temperature is raised you see a forest of other transitions starting from thermally populated states. And that's just how it works out in practice. So this shows terahertz spectra. So this is far infrared. This is the region between the infrared spectrum, the far edge, the long wavelength edge of the infrared spectrum, down into the microwave region is this interesting terahertz region. And at low temperatures, at 5 Kelvin, you see a single transition. There's a small splitting there, which we're investigating. But apart from the small splitting, we see a single line at 5 Kelvin. And then at higher temperatures, up to 100 Kelvin, then you see an additional range of peaks from these terahertz transitions. And if instead of helium-4, one has helium-3, because the atom is slightly lighter, or less massive, these energies are shifted up somewhat, but you get the same structure. And you can start to work on the theory of the frequencies and intensities of these lines. So there's some bars here indicate our theoretical model actually of this spectral structure. Neutron scattering is also very powerful and works in a similar way to some extent. Inelastic neutron scattering means that the neutrons lose energy or gain energy from the material through inelastic collisions with the nuclei. And you can analyze the energies of the neutrons and also get a sort of spectrum, which again shows you peaks corresponding to transitions between these different levels. And this also works out well with these peaks here due to the neutron scattering from the helium atoms and giving you spectral structure which we can analyze and understand. Now, what all of this is leading to for us at this point, and this is an aspect that we're very interested in, is a tool for determining the forces between the helium atom and the surface which encapsulates it. Because that's a type of non-bonded intermolecular force. And that's something for which there's very little experimental data. There's a great deal of computational methodology. It's a very important topic for understanding the properties of materials. Most matter is held together by non-bonded forces between atoms and molecules, dispersion forces, van der Waals forces, and so on. But and there's a high level of computational sophistication in estimating these forces, but it's hard. It's a very hard computational problem, very expensive to solve for molecules of reasonable size, and there's a great deal of uncertainty about it. What is lacking to some extent is experimental data, because these are extremely hard experimental quantities to measure. How do you measure the force between a single atom and the surface, for example? It's by no means easy. And these substances actually give you well-defined, controlled means to actually measure such potential surfaces representing these forces. So the idea is that one has materials consisting of uniform cavities with atoms or molecules inside them. The interaction between the atoms and molecules with each other and with the surface is described by potential, a potential energy function. The solution of the Schrödinger equation gives you some quantized levels. Transitions between those levels give you spectra, and measurements of the spectra then enable you to determine the potential energy function. And that's something we have done now for helium. So what's shown here is an actual potential energy function for helium inside C60. When the helium is at the center of the cage, its energy is defined as 0, but as the helium moves away from the cage center, its energy increases because of interaction with the cage, and the experimental data fits this sort of U-shaped form of the potential. And we're now in the process of comparing that with different quantum chemistry algorithms and collaborating with quantum chemists so that they can refine or test their algorithms. Yeah, so this gives you a route to something which is very hard to do, an experimental determination of the potential energy surface representing the interaction of a single atom with a carbon surface. Turning briefly to another system, this is water in C60, and as you can see here, there's just room for a water molecule to fit inside. Water has an aspect, a new aspect comes in, which is a very interesting one, I think, which is there are actually two different spin isomers of water. With nuclear spins parallel, that's called ortho water, and nuclear spins opposite, which is called para water. In fact, those of you who do NMR, and you will regularly take NMR signals from water as the solvent for many of your systems. In fact, you only see the NMR signals from one of those spin isomers, which is ortho water. That's the one which gives an NMR signal. The para water, which is 25% actually of the water, does not give an NMR signal. Now, in this, in relevance to this field, it's important to realize that the ground states of para water and ortho water have different energies. In fact, there's 34 Kelvin temperature difference between them. So the energy level diagram of water looks like this. I won't go into what the quantum numbers are here, but there are 3 quantum numbers for water. And you can see that there's an energy difference between para water and ortho water. In the thermal equilibrium, depending on the temperature of the sample, there's either more ortho water or more para water. So at high temperature, above 100 Kelvin, there's three quarters of the sample is ortho water and 1/4 is para. But at low temperature, below about 20 Kelvin, you get pure para water. And we've been studying actually the conversion from para water to ortho water in this substance, H2O-C60. And we've done that in many different ways actually, but one of the more unusual ways is just to measure the dielectric properties of this material, just by building a small capacitor, an electrical capacitor, in which inside the capacitor we have either water in C60, or we have an empty capacitor, or we have C60 reference material without water. And we could show that the dielectric properties of the material depend on the nuclear spin isomer composition of the water, so whether it's ortho or para water. And we could actually detect, without going into too much details here, this curve here indicates the conversion of ortho to para water, which is shown a bit more clearly here. The conversion from ortho to para water, which takes many hours at cryogenic temperatures, 5 Kelvin here. So this is a new physical phenomenon actually, that the electrical properties of material, the dielectric properties of material, depend on the nuclear spin state. And that's something which suggests possible applications in material science and for quantum memory and so on. With collaborators, some collaborators of ours have also performed some very sophisticated high frequency terahertz measurements, this time with very short terahertz pulses, which are only about a picosecond long. This work was done in collaboration with Mohsen Sajadi in Berlin. So by applying very short terahertz pulses to the sample and then detecting the terahertz emission after the pulse has gone by, one gets these oscillating decays of the terahertz emission, which you can analyze to obtain the terahertz spectrum. And these, this shows a plot of the terahertz spectrum as a function of temperature. And these terahertz peaks, these also indicate transitions between those quantized energy levels of the helium inside the cage. And that's something which is currently also being analyzed. Finally, I just show a few preliminary data on methane in C60, which is an exciting new material. This is about the largest single molecule which will go inside C60. It's very tight in there. There's just barely room for the methane to fit. But nevertheless, it can be made, and was made by Sally Bloodworth a couple of years ago. We're now exploring the properties of this material. This just shows some fairly basic NMR data from the proton NMR, which shows a single peak from the methane protons at an unusual negative chemical shift, because the methane is strongly shielded by the cage. Similarly for the carbon-13 of the methane, also strongly shielded. and some NMR data in which polarization is transferred from the methane protons to the carbon-13. So I think I probably more or less filled my time now, or spent my time. So I won't go on longer, but there's could be a lot more to say. We're hoping that the currently in the groups, there are intensive efforts to try and get other molecules inside, like ammonia or dioxygen. These will be very interesting substances with possible applications to masers and so on. But let me just make sure I thank the relevant people here who've really made the advances I'm talking about. So in particular, Richard Whitby's group, who've refined these synthetic techniques, developed some new synthetic techniques, and to our friends in Japan who started this whole area off. In my group, then, I particularly want to thank George Bakanu, who's my student, who has done a lot of these very nice measurements. And then we work together with several other groups on the infrared and terahertz spectroscopy, in particular Thomas Rome's group in Tallinn. The terahertz data on helium comes from their group, and Mohsen Sajadi in Berlin, I showed you some of that. And also Grenoble, the ILL Institute, Laura Lojava in Grenoble, who we work with on the neutron scattering, in particular Stefan Rolls. And I showed you some fine data from microscopy at Nottingham by André Klobistorff and his group. So with that, I thank you very much for letting me give this seminar. I hope you found it interesting. I'm very happy to answer any questions.
So thank you very much, sir. Any questions from the audience? No questions. Yeah, there were no questions.
Professor Levitt, that was a wonderful talk. I have a very simple doubt. Suppose that hydrogen fluoride encapsulated in graphene, sorry, not graphene, fullerene is treated with sodium hydroxide. What will happen?
I think nothing very much. There is basically the sodium hydroxide cannot penetrate inside the cage. It is possible to do exohedral chemistry on the fullerene, and there is a group in Spain actually whose name I don't remember, but they have demonstrated actually that the presence of the hydrogen fluoride can direct some of the chemistry occurring outside the cage. So the HF has an influence on the chemistry outside the cage, but does not participate directly in the reaction. Does that answer your question?
Oh, sure. I was just wondering if a proton can be just squeezed out of the fullerene cage using a strong base.
No, I don't think so. In fact, though, the Nottingham group has some evidence that irradiating the sample with an electron beam can kick protons out of the cage, leaving a fluorine atom inside, which would be another very interesting substance. But that's under investigation right now.
Okay, thank you. Thank you very much.
Thank you.
Sir, there is one question. Is it possible to encapsulate ions in the same fashion in C60?
Ions. Was that the question? Ions?
Ions.
Ions. Well, it's a very good question, actually. In the same fashion, probably not, because the chemistry, the procedure for encapsulation would not work with ions. Basically, the molecule is attracted inside the cavity by intermolecular interactions. I think I think it would be the thermodynamics would be strongly against ions entering the cage. But nevertheless, it's an interesting question, and I would say that topic is not known. It's under investigation. So it's not known if it's possible. I think it's probably not. And I don't know of any examples of when that has been observed to occur. But it might do. And that would be very interesting. Well, one should also, it's also worth noting that the C60 cage itself easily accepts an electron and becomes an anion itself. So it's possible to make anions in which the C60 accepts electrons, but still with a molecule or an atom inside it. So that will be a slightly different substance, but that has been done.
Okay. Can I ask one more question?
Of course,
yeah,
please.
You mentioned that when helium is encapsulated inside fullerene, the NMR spectrum, there's a change. C13 spectrum, there's a change. What about absorption spectrum?
That has been investigated. There's no... Do you mean the optical absorption spectrum?
Yes, exactly.
Yes.
Is there a color change?
There isn't. Nothing detectable, actually.
In fact,
this has been studied in great detail for water in C60. Because there have been attempts made to see if outer space contains water in C60, attempting to use the absorption spectrum. And in fact, some of the materials made in our consortium were used as tests to study the optical absorption spectrum of water in C60 in the gas phase. But unfortunately, there was no detectable difference from fullerene itself.
Okay. And one more question is the helium-4, helium-3 ratio in some of the meteorite that was found in Australia, that shows that that is extraterrestrial. Is it because of the isotope distribution that we conclude like that?
Well, this is not my field, but my understanding is that the isotope ratio is hard to explain without invoking an extraterrestrial source of the helium endofullerene. That the helium endofullerenes were actually created in the atmosphere of a carbon-rich star, which predates the formation of the solar system.
Okay. Thank you very much.
That is at least one of the current theories.
Is it possible to have this same similar work with in real?
Excuse me, I didn't catch that.
Instead of fullerene, can we use zeolite for this? Zeolites.
Zeolites. Zeolites. There are of course a lot of studies of molecules and atoms trapped inside zeolites, but usually these are channel systems. They're not completely closed cavities. And also it's much harder to make them very homogeneous. Not impossible, But there are similar studies, but they're of a somewhat different kind because the cavities are not completely closed, so they're more porous solids than closed systems. So slightly different field, I would say.
So shall I ask a question?
Of course, please.
So, what about the encapsulation of polar molecule and non-polar molecule? Will the encapsulation of these two types of molecules require the same conditions? Means, is it easy for both, or how can we compare the two conditions?
Yeah, that's another very interesting question. It seems that the polar molecules, H2O and HF, they both actually enter the cavity very readily, which was a bit surprising to me. Essentially, the net forces there's a net attractive force between the molecules and the surface. That may also be true for, actually that's also true for methane. So actually I'm not sure of the answer to your question, to be honest. I think, from my impression from talking to the chemistry people, there doesn't seem to be a great deal of difference between the behavior, for example, of water and the behavior of methane as far as entering the cavity is concerned, which is perhaps somewhat surprising, but that is actually how it is. Molecules like hydrogen and helium are actually more difficult simply because one needs high pressure to persuade the molecules to go inside. But that's more of an entropic effect that one has to battle against rather than enthalpy, if that makes sense.
Okay, sir. Sir, again, when molecules are trapped into this fullerene, the NMR, C13 NMR spectrum of this carbon-13 in the fullerene gets de-shielded.
Yes.
What may be the reason for that?
Actually, there are two mechanisms that we've identified. One is that the electrons on the noble gas atom slightly influence the magnetic field that the carbon-13 sees. And that is actually a small de-shielding effect. There's another effect as well, though, which is that the presence of the endohedral atom changes the geometry of the cage a little bit. The cage actually slightly contracts, and that also influences the carbon-13 chemical shift. So, for example, these shifts are temperature dependent because the geometry of the cage depends on the temperature. Essentially, the atom inside acts like a gas which exerts a pressure, and the higher the temperature, the more the gas expands and actually pushes out the walls of the cage, and that influences the carbon-13 chemical shift. So we can actually use the carbon-13 chemical shift as a sort of thermometer or a pressure sensor actually, for the pressure exerted by the single molecule inside the cage. Does that answer your question?
Okay, sir. Okay, thank you, sir.
Thank you.
So I hope there are no other questions. Thank you very much for the nice presentation. It was a very interesting lecture. So on behalf of the MATCON, I thank you, sir, for the lecture. Thank you, sir.
Thank you very much. Enjoy the rest of your meeting.
Now we are moving to the oral presentation. All participants are requested to be ready with the